Hello. Another typical problem for induction is proving inequalities for natural numbers. Let's start. Not necessarily for all natural numbers, an inequality, problem number 5. And here is the problem. Prove that for all natural numbers which are greater than or equal to 3, this inequality holds. And now you know already that some statements or theorems are just true from some point, not for all the natural numbers. And this is one of examples. So you see, I will write a short note here. Note that t of 0, of 1 and 2 is not true. So how would be t of 0? Would be 2 to the power of 0 is 1, is great, well, 2 of 0 is actually true, is greater than 0. So this is actually true. Because for n equal to 0 we get the left hand side 1 and the right hand side 0. This is actually true. But what about t of 1? What about t of 1? We get equality, right? Because 2 to 1 is equal to 2 and 2 times 1 is also 2. So 2 is greater than 2 is simply not true, right? And what about t of 2? For t of 2 we also get equality, right? So t of 2, the left hand side of t of 2 is 4, and it is definitely not greater than 4. So if I now wrote a non-strict inequality, then it would be fine. But you see that the statement is not true. The statement as it is with strict inequality is not true for n equal to 1 and for n equal to 2. So we will start with the base case for 3, right? And what about the base case for 3? For 3, the left hand side is 2 to the power of 3, it is 8, and the right hand side will be 2 times 3 is 6. This is obviously true, right? Here it was true. And now, how will t of n plus 1 look? Well, just take this inequality and plug in n plus 1 instead of n. What do we get then? We get 2 to n plus 1 is greater than 2 times n plus 1. This is what we need, right? Or you can write it in an equivalent way. 2 to n plus 1 is greater than 2n plus 2, right? So this is what we have to prove. And now we start the proof, right? So suppose that this t of n, and it is 2 to the n, is greater than 2n, is true for some n which is greater than or equal to 3. And we know that, for example, for n equal to 3, this is obviously true. So this is our induction assumption. And we have to prove that with this assumption, also the thesis for n plus 1 is true. So now I will take this pen so that you know that it's t of n plus 1 I'm working with. Then 2 of n plus 1, which is obviously equal to 2 times 2 to n, right? This is just the product rule for powers. And now I can use the induction assumption. So I will take this pen here. Here it is induction assumption. The induction assumption tells me that 2 to the power of n is greater than 2n, right? So this is greater than 2 times 2n, so 2n is coming from the induction assumption. And now I have to show that this is I have to show that this is greater than this number, right? Twice n plus 1. And I see that it is greater than 2n plus 2. And why so? Well, let's verify that it really is true. So this inequality, which I marked now, is 4n is greater than 2n plus 2, right? It is equivalent to the inequality 2n is greater than 2 or 2n is greater than 1, but our n is greater than or equal to 3. So this inequality really is true. And we then get our thesis for, maybe wrong color, it will not be visible. So you see what we got here. We got that 2n plus 1 is indeed greater than 2n plus 2. And this is exactly the thesis for n plus 1. So then the principle of mathematical induction tells us that we are done with this proof. Thank you for watching. Bye bye.